So we spoke about the t-distribution and how we can use the probability density function of the t-distribution to work out whether the t we calculate for our samples is actually big enough to reject the null hypothesis. And I'm going to give you an example of a sample A versus a two-sample unpaired t-test. We have two samples here. We have sample A, we have sample B, and we want to know, that's that hippo versus elephant example, right? We want to know, are these two populations different? And I can talk about things like sea level rise. Is the global mean sea level now significantly, and we use the word significantly to indicate that we have statistically shown that these two populations are different? So that's the word significantly has a meaning in science, and that suggests a statistical test has been applied and found that the null hypothesis is different. It is significantly different. So that's a significance value. The p-value was lower than 0.05. It is significant. So is there a significant difference in the global mean sea level in the last decade relative to many years ago? Okay. So has sea level risen significantly? So if I look at this plot of global mean sea level, we can see there's a steady rise in sea level in the past centuries, decades. And there is a point where actually the rate of rise has increased. And it's increased from about 0.6 millimeters per year in the beginning of the 20th century to we're at like above 3 millimeters per year. The rates of change in sea level vary in different parts of the world depending on the changes in the heating rate of the oceans. And what we see on average, global mean sea level is not only sea levels rising, the rate of change is rising as well. Okay, so lately we've been heating up quicker, right? And sea level is linked to temperature through a few different ways. I mean, like, first of all, the water is warmer, the ocean is warmer, and it's expanding thermodynamically. And then there is addition of fresh water from landlocked ice, right? That's being poured into the ocean. So we have an increase in sea level, and I'm interested to know, I'm going to take a sample from here and a sample from there, and I'm going to see whether they are significantly different. Because if I take a sample of sea levels from here, I'm going to have some sort of mean and standard deviation around that mean. I'm not comparing one number to one number, I'm comparing a population of numbers to a population. So to do a two-sample t-test, I have two populations. They must be independent of each other. So yesterday's sea level and today's sea level, they're not independent of each other. I need to put some distance between those measurements. I'm going to compare the beginning of the century to the end of the century. Right? So what I'm trying to do is to test for the difference between two means. I'm going to measure the difference between two means using that t statistic. Remember, that took into account the difference between the two means. Okay. It took into account the standard deviation around that mean. It took into account the population size from where I've extracted those means, right? So we had a t that had all of those in it. Now I have a null hypothesis that says the difference in the means is such and such. In my case, I'm saying 0. And I have a an alternative hypothesis. One of them is that the difference between the means is not that number. It's not different. In my case, I'm saying sea level, beginning of century minus sea level, end of century is going to give me 0. And the alternative is saying not so, not 0. And what I'm trying to determine is whether the means of these two samples are different. And remember, we said that if I have a t-value that's above 1.96 or 2, I'm going to have, this is where my 95% confidence interval sits for the hypothesis, the probability. So I'm looking to see whether that bit of the, where my, so I'm saying these two are different, if that bit is different. Hold on, coming back to it here. So I can look at sea level in all sorts of parts of the world. There's the permanent surface for mean sea level. There are a lot of, we basically measure sea level in a few different ways. One of them is just basic tide gauges. So most ports would have a tide gauge in them because the port really needs to know the depth of the water and how it changes with the tides, because ships need some clearance depth, right, to come in. So they monitor this all the time, and they have for centuries. And there are places on Earth where we know what the sea level is, and it's monitored a few times a day. And these days it's all digital. And we have a good record, and in Australia, Fremantle is the longest record of sea level, and then we can have a mean sea level, a global mean sea level, and we can look at how that changes over time. This is where that data comes from. So here are the two regions I'm looking at. Okay, I took sea level, which is this symbol here, from 1990 to 2010. And my null hypothesis is that it's the same. So this is the tide gauge at Dover. I'm going to look at the sea level from 1960 to 1980. Dover is on in England, of course. Sorry, I should have clarified. The null hypothesis is no, that it's actually bigger than that. That today sea levels are higher. I could also just say it's different. I don't have to say bigger. So I have a region of sea levels down here. I have a region of sea levels down there. I'm going to ignore this one in the middle. And I'm going to take, of course, the mean and the standard deviation of those. Here's my t, the difference in the means, divided by the standard error. Remember, the standard error was to do with the standard deviation and the populations. Now, for each data set, I'm going to calculate the mean and the variance. Okay? And I'm going to have, this is my t distribution, and this is a two-sided t distribution. And this is my area of rejection of the null hypothesis. This is the area of acceptance of the null hypothesis. I'm going to have one-sided t-test. And now you see that I still have 5%, but I can bank them all on one side. So I have a t-value at a lower level can already indicate that the two populations are different. In this case, we're looking at the hypothesis suggested a one-sided t-test. I was actually looking for, is it bigger than? Almost always we're going to have a two-sided test. Is it different? Now we need to calculate the degrees of freedom. We have one population minus 1. Remember, we spoke about the degrees of freedom being the population size minus 1, plus the second population minus 1. That's our population size. That's the df. Okay, and the df determines the shape of the t distribution. Or more written out, we can look at 1960 to 1980, 1990 to 2010. Here is the mean. Here is the mean. Here is the variance. Here is the variance. Here are the number of samples. Here are the number of samples. Okay, they are annual measures. And I can take my t and put those in. Okay. Fill in the blanks. Okay, so that's the square root of the variance. Okay, the standard deviation squared. So 605, 608, 20, 20. Here is the t statistic I've calculated. This is a t that is some sort of statistic that represents difference in needs. Okay, so it's a fancy way of saying the difference in needs. Here are my degrees of freedom. I can look at the probability, and I can look up a table and see what the probability of getting a t of 8.98 is with that kind of shape of distribution, with a df of 38. And I think you already remember that we said that a t above 2 already indicates a significant difference between those two means. We are way inside, we have a very high t here, and that's because sea levels have actually risen quite a lot. If you use R, you can use a function called PT, and work out what the probability of getting a T of 8.98, so this is the cumulative distribution function, when the shape of that distribution is that of a degree of freedom of 38. I mean, so we're already talking about a normal distribution, and it will spit out what the probability of that is, and that's 0, or maybe very close to 0. So it's very hard to obtain a T like this if these two populations were actually the same. So this T is so big that there's no way we can have a population that has the same mean, but we actually sampled and we got a slight variance, and we didn't detect it. There's no way there is the same mean, and we didn't detect that. We have detected a difference, and it's a true difference. The old school, the no computer way, like I said, was to look up in a table so I can have what the T's are for different degrees of freedom. So these are different degrees of freedom, and these are different confidence level. Okay. So where is my alpha? Remember we said, what am I accepting? We're talking about 0.05. So that's this line and this is the value I need to exceed. Okay. So if I have, in this case, I need to exceed a value of I can't see from here, but 1.8 something. I have 8, right? I have 8.98. I'm way in excess of this, okay? The mean sea level at Dover the past 20 years is significantly higher than the mean record for 1960 to 1990. Okay, and I've conducted that. To do this in R, and you'll do it in computer class, I just write it. I mean, it's so much quicker, which is why R is wonderful. So remember, I can use the hash to just write text. Okay, so I can describe my line. I can describe a line. When here is this is the command you would be using, and this is how it would look like on the console. So I have a prompt here, and I can define my year 1960. So here I have a data set called sea level, and year 1960 is rows 1 to 20, comma, all the columns. Again, remember we said cells look like a square, right? And then I create another vector, which is called the year 20, or another data matrix that is called the year 2010, and it is those rows 30 to 50 of the same data set. Okay, so now I have 2 different data sets. And I conduct a t-test, which is part of the standard R language package that comes along. So you don't need to install another library. This comes with the stats library that comes with R. So it knows what t-test is. You open your brackets. Who are you comparing? I'm comparing year 1960, the second variable, which is the sea level, because I think the first variable is years, to year 2010, the second variable. That's it. Hit enter. Or run this code. And what we get is, this is the output. It says, I've conducted a 2-sample t-test. It's called the Welsh one. These are the data sets I've used, 1960 and 2010. Good, that's what we wanted. Here's the T I've calculated. It's negative 8.59. The negative comes from the fact that it depends who you subtracted from who. It's symmetrical. Okay, I can have one population bigger than the other, but the other population is smaller than the first one. Okay. Here are the degrees of freedom it calculated. This is the p-value it came up with. The chance that T would be exceeded in a population of 2 exact sea levels is minuscule. Okay, it's 0. So what it's saying is, true difference in means is not equal to 0. Okay, here was the 95% confidence interval and of the differences. Okay, our difference is actually much bigger than that. And this was the mean of X, the mean of Y. And like that's giving us a little bit more information, but really what we need to know is that we rejected the null hypothesis. We accepted the alternative hypothesis of H. I'm going to give another example. So we have student scores. We have a student has submitted 10 assignments, not usually. And there's student A, and student B. Okay, and one of the students did well in some assignments. One of the students did well in another assignment. This time, we don't have just a random population of assignments, but they're actually what we call paired. So for assignment 1, we have one value from student A, one value from student B. For assignment 2, we have one value from student A, one. So we don't just, what we can look at is the difference in assignments. Okay, so maybe assignment 4 was harder, maybe assignment 4 was. We are reducing the variance by pairing the two samples. So when we can, we use a two-sample paired t-test. And you can understand the pairing best by giving examples. It's when they've both submitted the same assignment. It's the same person getting a before and after treatment, you know, measuring hair amount before and after hair loss treatment on that same person. Okay, so you are reducing variance because you're using the same person. And then you have 10 people, but they've all done the before and after. So you can look at the difference before and after, or you could look at, they're all getting the same assignment, there's 2 of them, it's paired. Okay? So here's student A, here's student B, these are the scores they got, they did very well, both of them. And this time we have sites that are paired, for example, we have restored or unrestored salt marshes next to each other in different parts of the country, okay? But we have a paired system in each salt marsh. We have an area that was restored and an area wasn't. But it's still a salt marsh that's sitting in Victoria. So we can look at samples in group A and B, can be paired. They are the same number of samples. They have to be the same number of samples. We can't have one of them not doing assignment 7, one of them actually doing assignment 11 and the other one not. Okay, so we need to make sure in our paired design has to have the same number of samples in both groups, with each having a matching sample in the other group. Unpaired means, it's sometimes it's easier to understand the unpaired. It means that group A and B cannot be directly paired. Okay? Say I've done, I just want to know how good am I at uni. I didn't do the same unit as you. My assignments can't be paired to yours, but I can have a mean mark on my assignments. I got a 7.5. You got a 6.9. I mean, like, well, because I'm a better, but there's, am I actually statistically significantly better than you, or is there so much variance that it's really impossible to tease apart this difference in mean? But we don't have a direct comparison, okay? We didn't both submit the same assignment, okay? So that's unfair. Okay, so in this case, we have a slightly, we use the same t-statistic, okay? It's still the same t-statistic, only this time we have a population of differences rather than and a standard deviation of the differences rather than a mean of the population and a mean of the population. Okay, we also have a different way of, now we have a population of differences. Okay, so we have a smaller amount of degrees of freedom, okay, because we don't have 20 anymore, we actually have 10 differences. We take away 1, we have 9 degrees of freedom. This is the mean of the differences, the standard deviation of the differences. Okay, so that's the difference between the students at each assignment, the mean and the standard deviation. If you do it in R, it will be a paired t-test. We're going to get to that in the computer.